Hey folks, happy building to everybody out there, and thanks for tuning in again. This is Shop Talk number 46. Man, I can't believe how fast this goes by. And I just want to say thank you for tuning in, and thank you to Jim Deeming for that wonderful opening theme music there. If you're into Chet Atkins finger picking, thumb picking kind of stuff, then jimsguitar.com is what you need to check out. Jim's a fantastic player. Jim had an accident here recently, him and his guitar. In fact, I think I've got some pictures here I can show up. Let me see if I can just pull that up here. Jim was out at a gig, and it must have been a pretty exciting gig, as you can tell there. Things happen. And that's one of my guitars that I've made for Jim. And Jim, I'm happy to report that I have retopped that guitar, took the top off, took all the kerfing off because some of it was pretty busted up there in that area, and have retopped it. And it is only a matter of time until I get that thing back to you. We still have a little bit more before I can get it back to you, but I've been working on it, and the new top is on, the new binding's on, it's been sprayed, we're into the cure time. So it will be available soon. Just don't know an exact date yet. Thank you to all of the sponsors from the Luthier Academy, and I'm going to bring them up here and show you those. They help keep the lights on here at O'Brien Guitars. And we'll start with Royal Lac. We also have Acoustic Coffee, Total Vice, that makes the sound hole clamp that you guys see me using here in the shop. Pacific Rim Tone Woods, and their sonically tested woods, just fantastic. I have several students come in and start building with that. StuMac, great products, lifetime guarantee from them. Glue Boost. We also have Skyscraper Guitars. Skyscraper Guitars is the most recent sponsor here, and they have the new version of my neck angle jigs available, and of course, the great products available from Elevate Lutherie. So make sure that you please, if you need a product or a service, check these folks out. They all have been vetted here through the Luthier Academy, and they help bring this broadcast to you. Also, while you're over there at the Luthier Academy, go ahead and check out all of the things that are available. I have got over 50 online courses available to you now. A couple of them are done by my guest that's going to be here in a few minutes, Trevor Gore, all the way from Sydney, Australia. But there's a great amount of information there in online courses, things that's taken me a long time to put together. Also, if you take a trip over to the resources page, Cesar and I have spent quite a bit of time putting that together. There's a lot of great internal links and external links that will take you to websites and have great videos and articles and things that are great resources to us here as luthiers. Also, if you go to the videos page, you can see all of the Luthier Tips du Jour videos that have been released, a lot of other videos that I have there. So a lot of great information. So take advantage of that stuff. I mean, it takes me a long time to put that stuff together. So go ahead and check it out. And once again, thanks for tuning in. I'm always amazed at how our reach is here with the internet. I mean, I just looked at this here, and the first person that checked in here is all the way from Tahiti. My God, I don't even what it's like. I guess he's over there by Trevor. Trevor is like 10 o'clock in the morning on Tuesday for him. California, Spokane, Washington, Pensacola, Florida. Rob right here in Denver. Sam the Grasshopper, I don't know where he's from. San Francisco, Flagstaff, Arizona. There's somebody from Los Angeles, Mexico, somewhere in Mexico, we don't know where. Kentucky, Cesar's all the way down there in Brazil. We'll check in with him in a minute. Tony, there's Tony there in Elizabeth. He was here in the shop here recently. John from Colorado, New York. There's another one from Australia. There we go. Anyway, Alaska even. Oh my God. Anyway, thank you everybody for tuning in. There's a couple of guys there from Alaska. Amazing. Honolulu, Hawaii. Man, this is just amazing. If you guys have questions during the stream, go ahead and put them in the chat box, because the last time I had Trevor Gore on, it got pretty intense, and we went all the way up right to the hour. We had to actually cut it off and left a lot of questions hanging. So if you have questions, go ahead and put them in the chat box. I will monitor them, and we'll try to get to as many questions as we possibly can. Let's pop in down in Cerquillo in São Paulo, Brazil. Let's talk to the lovely Cesar and Manuela. There they are. Thank you for tuning in.
Hello.
Thank you, Cesar, and Manuela for tuning in again. Cesar, can you please tell us what the drawing is going to be today and how people can enter for the drawing?
Yeah, so today, as usual, participating is quite easy. All you have to do is click the link at the top of the chat box, let us know your name and email. And today we are going to give away two of Trevor Gore's courses, the Falk 8 racing course and the guitar analysis and testing course. So a lot of great material.
All right, so you guys click on the link there at the top of the chat box, and you guys can enter the drawing. Cesar will be back at the end of the broadcast. Don't go to sleep on us now. We'll be back.
No. Thank you.
All right, so my guest today is no stranger to the guitar building world and no stranger here to the Luthier Academy and the Shop Talk live stream. He's been on before, actually a couple of times at least. And he just recently was here in Colorado, and we gave a series of master classes together here in my shop. So here we go. And here comes Dr. Trevor Gore, all the way from Sydney, Australia. Thank you for tuning in.
Hello, everybody. Hope you're all well.
All right.
Hey, Robert,
I know you've been
hardly a Beatles mania welcome there. I didn't hear any screaming girls.
Well, those are coming. The belly dancers will be here shortly, right?
Okay.
All right. Well, Trevor, I follow a lot of what's going on the internet, trying to keep my hand on the pulse of things. And there's a lot of stuff going on, a lot of buzzing going on these days about modal tuning and how you can make your guitar better. And of course, Trevor wrote a couple of books on the design and build of a guitar. And so I said, well, let's go directly to the source. He's the source for all of this information that a lot of people are putting out. So I've got some questions for you that people have sent to me, Trevor. If you don't mind, I'll go ahead and just start asking questions. I think you have a little PowerPoint presentation ready to go as well.
Inevitably.
Okay. All right. Well, let's just bring Trevor up. You don't need to be looking at me, so we'll just keep Trevor up. Oh, my God. Look at that guitar collection in the background there. That's fantastic. So, Trevor, talking about acoustic measurements of wood and guitars, what do you aim for when you build a new guitar? Is there something you shoot for, a way to measure stuff? And how do you do it?
Yeah, well, let's dive into the PowerPoint and see if we can pull some of this up. I mean, my objective when I'm building guitars is, first of all, to get the monopole mobility right. And I say right, not necessarily high. If you want a really responsive guitar, you need high monopole mobility, and it's a measure of the sensitivity of the guitar and a measure of its potential loudness. So that's one thing I'm aiming for straight away. Second thing is the evenness of the sound, and that depends on avoiding wolf notes. So that's placing the major resonances off of scale tones. And the third thing I'm looking for is musicality. So that's an alluring sound, which is dependent on having a high peak density in the frequency response curve, and also correct intonation, getting the thing to play in tune to the equal tempered scale rather than fairly well out of tune, particularly on the low frets that a lot of acoustic guitars suffer from. So those are the three things that I try and get to when I'm looking for to get a guitar on track. There's a couple of things that I've not mentioned there, and that's the basically the setup of the guitar, the playability. I assume most people can manage to get the playability right, and the other thing is the structural integrity. So I'm sort of taking those two aspects for granted. So I'll not be talking much on those at the moment, but critically they're important, but I won't be speaking much on those today.
All right, Trevor, I'm going to put your screen of the PowerPoint. I was a little late on the draw there and clicking on the buttons. I'm going to put that back up again so people can see that. So the three things that Trevor just talked about, the objective of a responsive guitar is the right monopole mobility, and we'll go into what that is here in a minute, evenness of sound, and then the musicality. So, Trevor, are there ways to measure that? Now, I already know the answer to that, of course, because we put together an online course. If you go over to the Luthier Academy website, there is one of Trevor's online courses. It's called Guitar Analysis and Testing with Trevor Gore, where he shows how to set up the hardware and the software to run these tests. So, Trevor, could you go into just a little bit about, first of all, what is monopole mobility? Is that a name that you've coined, or is that fairly well known? And how do you measure it?
Yeah, monopole mobility is a name that I came up with because it's a bit of a sort of hybrid type of a measurement. It's a measurement that's relatively easy to do and gives you a fairly stable number when you calculate it out. You know, it's something that's repeatable. There's probably a more correct way of measuring monopole mobility, which I won't go into because it's somewhat difficult and somewhat more mathematically intense. So to measure monopole mobility, you need to know two things. You need to know the stiffness and you need to know the equivalent mass. So that's the equivalent stiffness and the equivalent mass of the monopole mode of vibration. The stiffness and the mass together give you an indication of mobility. And measuring that on the monopole mode of vibration, we use the monopole because that's the most effective sound radiator of the whole guitar. So if you can get an indication of how well the monopole mode of vibration moves, you get an idea of the overall responsiveness, sensitivity, and potential loudness of the guitar. So if we look at that, the things we need to know are measurement of K, which is the stiffness of the guitar, and M, which is the effective mass of the monopole mode. And we use this little piece of kit here. It's a beam across the guitar with in the old days, this was a dial indicator. Here it's actually a tire tread depth gauge. And I'm loading right through that gauge onto the bridge of the guitar. And if I put a mass or a load on this platform here, that gets directly transferred to the top of the guitar. So this is a bag of lead shot, weighs about 1 kilogram. Put it on here. You need to actually convert the load to newtons. So 1 kilogram is around 9.81 newtons or 10 newtons. Put that load on, measure the displacement S, and the load P divided by the displacement S gives you the stiffness. So that's newtons per millimeter or newtons per meter stiffness measurement. And look, reading this gauge here, I've got something like 0.15. So it's moved 0.15 of a millimeter when I put that weight on there. So that gives you the K part, the stiffness part of the equation. We also need to measure the effective mass. And we can do that by measuring the effective mass of the monopole mode of vibration uncoupled from the other modes of vibration. And we uncouple the top mode by blocking the sound hole to uncouple, which uncouples the Helmholtz resonance. And as it happens, it also uncouples the back from the system as well. So if we block the sound hole, tap the guitar, we get a frequency F here. And we measure that with some frequency measuring equipment, usually something like visual analyzer, but anything that will give you a frequency number is fine. So we can measure this frequency, and the frequency is proportional to 1/2 pi the square root of the stiffness divided by the mass. That gives you the natural frequency of a mass on a spring, which is essentially what this is. So we've already measured K, so we know that from here. We now need to figure out what M is, but we've measured F, so we know everything in this equation except M. So we can turn this equation around, figure out what M is, which is K over 2 pi F squared, and then we can get the monopole mobility, which is 1/2 the square root of K times M. And that gives us a measure of the responsiveness of the guitar. And if you want to increase the responsiveness of the guitar, so you want to make the monopole mobility higher, you've got to decrease either or both of K and M. So if you want a more responsive guitar, you've got to decrease its effective mass and decrease its stiffness. And that makes monopole mobility go up and more responsive guitar. But another thing you have to keep in mind is the fact that the resonant frequencies of the guitar is dependent on this equation, K over M. So the greater you make K, the stiffer you make the guitar, the resonant frequency rises, and the lower the mass of the effective mode of vibration, the frequency also rises. And if you want to target a particular frequency, you've got to get these two numbers in the right relationship, and you've got to lower them in proportion in order to make the monopole mobility higher. So that was a quick exercise in probably year 8 of maths or something like that, which will give you these sort of relationships. So that's the measurement of monopole mobility. And if we look at what good numbers are on classical guitars, a really good guitar is somewhere up in the sort of 32 level of monopole mobility. And these guys down here, there's some pretty famous makers, Spanish makers down here. In those days, the ability to make really high monopole mobility guitars was somewhat limited by the availability of materials, because to get these to work, you almost certainly have to incorporate carbon fiber into the structure, where of course none of these guitars had any carbon fiber in there. So that's classical guitars. Typical levels are around 20-ish. Good levels are somewhere in the 30s. If we move on to steel string guitars, which have to take more load and are a bit stiffer, really good numbers are in the low 20s. Typical numbers are in the 10 to 12 mark. And there's a massive... These guitars down here were basically the best samples that we could find of these types of guitars. So these are the sort of high monopole mobility versions of these models of the guitars that were available to us for testing at the time. The problem is that all these guys making all these guitars will tell you that these guitars were the next best thing since sliced bread in terms of responsiveness and loudness and playability, etc. But they're leaving a lot of capability on the table, and that's what I call the conspiracy against guitarists. It's the difference between what you can buy in a high street and what you can get if you really put your mind to it and work on your monopole mobility of the guitars. So these guitars are sort of highly responsive. These guitars, nice guitars, but somewhat less responsive. So that's how you measure monopole mobility. I mean, we can go into great depth here. I'll go on evenness of sound, and that depends on avoiding wolf notes. So it's placing the major guitar resonances off scale tones. Here's a frequency response of one of my guitars. It's a medium body guitar, medium sized guitar. I built this a long time ago, 2007. The major resonances to get right are the low order modes. That's the T111, the T112, and the T113. And those are these three peaks here, which correspond to this mode of vibration. That's the T11 mode. There's three of them, one driven mainly by the air, one the main top resonance, and the other is the top coupled with the back. So that's these three monopole modes of vibration, which are these ones here. And so the trick is to make sure that those three resonances are not on scale tones. And if we look at the note frequencies, we select the mode frequencies from the outside columns to best avoid wolf notes. So in this table here, right down the middle, let's take A, we've got 110. So an accurately in tune A note is at 110 hertz. If you go 50 cents off, you're down at 107 or 113 if you go sharp. So what you want to do is try and select frequencies from these outside columns, which are the furthest away from the scale tones down the middle, and avoid putting your resonant frequencies on these scale tones. If you play, say, an A note on a guitar with a resonant frequency of 110 for the, say, air resonance, that's going to be a really loud wolf type note and not very good. So when you're selecting those mode frequencies, we're taking numbers from these outside columns, and they vary a bit for the different styles of guitars. And you select any of these numbers here. You can't totally mix and match them. For example, it's not a good idea usually to have an exact octave separation between the T111 and the T112. So you wouldn't go 90, 180, which is exactly an octave separation. You'd go 95, 180 or 90, 190. And generally, a good rule of thumb is to keep 4 semitones separation between the T112 and the T113. So that covers off on the evenness of sound. It depends on avoiding wolf notes and placing the major resonances off scale tones. And finally, for this presentation at least, we'll look at musicality. And that's making sure that the guitar has an alluring sound. And remarkably, that can be correlated to various aspects of the frequency response curve, particularly in having a high peak density. So if we go back to this frequency response curve, you'll see there's a lot of peaks in here. And a couple of guys, Matthews and Kohut, were researching functions of violins and trying to come up with an idea of what made an alluring sound for a violin. And they found that between 20 and 30 peaks in the frequency response up to 5 kilohertz, irregularly spaced with respect to harmonics, gave the most subjectively pleasing results. And that actually works okay for guitars as well. So basically what it means is cram as many peaks as you can in this sort of region. You're a bit out of control beyond the kilohertz, but cram as many as you can in down this area here. And irregularly spaced with respect to harmonics of the strings, what that means is don't put them on scale tones, as we said before, and that gives the subjectively pleasing result. And the way you get a lot of peaks in here is to make a live back guitar. And so a live back guitar will give you effectively more tone. A non-live back guitar doesn't have these peaks in, doesn't take energy out of the spectrum, and gives you a louder guitar. So a live back gives you tone in round numbers, so to speak, and a non-live back gives you volume. Second thing we talked about was guitars that play accurately in tune to the equal temperament. That was another piece of work done in the research field by these guys I mentioned down here back in 1999. And they found that amazingly, guitars that play in tune are preferred. A guitar tends to play out of tune on these low frets for a couple of reasons, but a way around that is to do both nut and saddle compensation, and that's a pretty important part of getting guitars to play accurately in tune. So as well as compensating the nut, you compensate both the nut and the saddle, and I think you can probably just see these cutbacks into the saddle here, which is the saddle compensation that goes with the nut compensation. And details of how to do that is fairly, and why it works, is fairly mathematically complicated, but it does work. Every guitar I've built has had a compensated nut and a compensated saddle. If you do conventional saddle-only compensation, even if you do it perfectly, it tends to leave the lower frets playing sharp. So this is a mapping of the fretboard for each string on each fret for a guitar that's been tuned to be no sense out of tune on the 0 fret, i.e. on the open string, and exactly in tune at the 12th fret. And if you do that, you find you're playing sharp in this region around here. And the main reason for that sharpness is that the pressure you need to hold the string on the fret is a certain amount of pressure. And because the frets are wider apart in this part of the world, frets 1, 2, and 3, the string goes farther down towards the fretboard between the frets, and therefore pulls the string tension higher, and it goes sharper. As you get towards this neck of the woods, up in the higher frets, for the same amount of force, you've got a smaller span between the frets. And so you don't press as much between the frets and you don't pull the string as sharp correspondingly. So that's why it's like that. And that's why compensating the nut helps. And if you compensate the nut for typical fretting pressures, you can get the guitar to play in tune pretty well right down the fretboard with a minor wobble down here, which is actually less than 1 cent. It's a maximum amount of tuneness comes out to be about half a cent, which is pretty damn good. So that works really well. So that's the...
Trevor, can I ask you a question real quick?
Yeah, go for it.
Yeah, I get this question a lot. And people all the time ask me, so, okay, if you compensate on the nut, open tuning, open strings, okay, but as soon as you fret the string, doesn't it cancel out that compensating you did on the nut? And I know what you're going to say, but I'll just let you say it.
Yeah, no, it doesn't. The reason being that imagine you've got the guitar with no nut compensation at all, and you've tuned the guitar, and it's perfectly in tune on the open string. Now you move the nut forward towards the first fret. The consequence of that, to play in tune, you've now got to tune the string slacker. You've got to drop the tension of the string because you've shortened it for it to play in tune. Now you drop the tension on the whole string, and if you drop the tension on the whole string, it's going to play flatter on every fret. So that's what happens. So with nut compensation, takes you down exactly the same number of cents on every fret. So if you move the nut towards the first fret 1 millimeter, that's equivalent to dropping the frequency on each fret by about 3 cents.
Okay. Folks, this is a lot of great information here. I hope you're appreciating this presentation that Trevor's put together. I've sat in on Trevor's modal tuning class 11 times. He's come here and given that class 11 times. And it is like drinking from a fire hose. So if you folks want to delve into this a little bit more, just go out to his website. Let me just pull up his website real quick. This is goreguitars.com.au because he's in Australia. And down there at the bottom, you can click on a link called The Book. Let's see if I can get that to pull up here. There you go. And it talks about the background of the book, the design volume, the build volume, and all of this great information is not only in the book, but it's been proven mathematically. And I asked Trevor one time, because I'm not a numbers guy, I asked Trevor, I said, Trevor, why all the math? Why did you put all that math in there? And Trevor's response was to me was to prove to the skeptics that this is the way it's done. So he's proven it all mathematically as well. Trevor, I'm getting a lot of questions coming in here through the chat box. I'm going to let you go ahead and continue with your presentation, though, if you want, and then we can get to the questions at the end, or you prefer I feed them to you as we're going along?
Oh, fire a couple of questions in there, Robbie, because me and PowerPoint probably get a bit tiring after a while. So
okay, well here's one. Let's see, I just lost it. Where'd it go? Oh, let's see. That was talking about the nut compensation. Here we go.
Yep.
Let's try and pull this one up. This one is, could you explain what the compensation is from a mathematical point of view? And you kind of did that. So if you think you've answered that enough, that's fine. If you want to go into it in more detail, just fire away.
Yeah, I'll leave it where it is at the moment, because there's a 20-page chapter in the book on how to do compensation. And there's some very mathematical methods in there of how to make it work properly. And there's also some sort of simpler methods which aren't quite as good, but actually do not a bad job. And I'll explain just one of those simple methods. And one of those simple methods is, hey, if you figure out the amount of compensation you need for saddle-only compensation, and let's, for example, say we're just talking about a steel string guitar, you might need something like 4 millimeters on the 6th string, total compensation for saddle-only compensation. Now, a quick and dirty method into nut compensation, nut and saddle compensation, is to take that number, 4 millimeters, divide it by 2, and put half of it, that's 2 millimeters on the nut end and 2 millimeters on the saddle end. And it's not a bad approximation to proper nut and saddle compensation. And the reason mathematically how it works is all in the book. And without going through 20 pages of mathematics, I'm not going to demonstrate it here now.
Okay, here comes another one. This is from David Ling, our buddy up there in South Dakota. He's also sat in
Oh, yeah.
on your class before. When
Yeah, hi,
selecting
Dave.
a top, assuming all else is equal and assuming you can measure accurately, how important is acoustic radiation coefficient and Q in selecting top wood for a specific acoustic type? That's a great question, Dave.
Yeah, okay, let's go with the acoustic radiation coefficient. That's basically a measure of the responsiveness of the material. And it's a pretty good measure. It's basically the square root of the Young's modulus over the density cubed, and gives you a good indication of the quality of a piece of wood. There's a few methods of assessing the quality of wood. I won't go into the details of all of those, but this is not a bad one, the sound radiation coefficient. So if you can find a piece of wood with a high sound radiation coefficient, you can make a more responsive guitar. So if you're building a classical guitar, for example, you'll probably choose a piece of wood with a high sound radiation coefficient. So you'll save your sort of best wood for classical guitars because you're always looking for as much volume as you possibly can. On a steel string guitar, if you're making, say, a finger picking guitar, you might also go for a high sound radiation coefficient piece of wood there. But if you were making a strumming guitar and want a bit more headroom, you might drop down on the sound radiation coefficient. And certainly if you're making something like a stage guitar, where you're building a guitar that's going to have a pickup in it, you probably don't want high sound radiation coefficient wood anyway, because all you'll do is make yourself a big microphone and suffer lots of feedback. So you can choose your wood for the specific type of guitar you're wanting to build. So that's the sound radiation coefficient bit. If we go to the Q bit, that's pretty interesting. I've done a lot of work with Pacific Rim tone woods on measuring Q and studying the effects that Q has on the actual sound of the guitar. And on the one hand, excuse me, on the one hand, there's a lot of people that can hear the difference between a high Q guitar and a low Q guitar, both on steel string guitars and classical guitars. And to me, that's quite an important difference. But there's also a lot of people who can't hear the difference. And if you do blinded tests, which Pacific Rim tone woods have done in conjunction with myself and a lot of very smart guys at the University of Dresden in Germany, in an anechoic chamber and all the gear and whatnot, and a whole load of listening tests. They found that basically there was no significant difference between low Q and high Q guitars that could be detected in listening tests. Now, that's what you get if you ask a lot of people, and that's a paper that's about to be published. The paper's written, the paper's submitted. I think the paper's been accepted. Not sure exactly when it gets published, but it won't be long, I suspect. So that talks a lot about Q. And on the one hand, there's a cognoscenti who appreciate the difference, and on the other hand, most people don't really hear much difference. But there's a video on my website that has three guitars played by Miroslav Tadic, where the only difference between the guitars is the damping coefficient of the top. And he plays those three guitars. You'll see this one that's, I think, is on your screen now, which has a B stuck on the headstock. There's B, R, and Y standing for blue, red, and yellow. And that video goes for a while. He plays three guitars, one after the other. They're basically absolutely identical in terms of their frequency response curves. The only thing that's different is the Q value of the tops. So it's a pretty high quality recording. So if you put that through some very good speakers or a good headset, see if you can hear the difference.
Trevor, I also have put the links to a couple of those videos in the video description here on YouTube. So if you want to click
Yeah.
on those links, you can be able to hear those and compare those three guitars. It's a very interesting listen. So make sure you do that. All right, I think we answered David's question there. Let me see if I can, unless you
Right.
want to add some more there to it.
No, that'll do for that. Thanks for your question, Dave. Good one.
All right, here comes one from Alexander. Let's see. Hi, Trevor. In your book, it says that a good bridge weight for a steel string guitar is around 16 grams. Would that be the same for a dreadnought? And what happens to the sound when you go to a lighter bridge?
Yeah. Well, you got to consider the bridge in relationship to the whole guitar, and the bridge is, on the one hand, somewhere to anchor your strings. On the other hand, it's also the stiffest and heaviest brace on the top of the guitar. So the stiffer and heavier you make it, the stiffer you make it, the top frequency goes up, and that's the T112. And the heavier you make it, the top frequency goes down. So if you're looking for a guitar with a lot of headroom, you'll probably go for a heavier bridge. At the same time, you've got to keep the resonant frequencies in the right place. So the more you increase the bridge mass, the stiffer you have to build the guitar in order to keep the resonant frequencies in the right place. And as the stiffness and the mass go up, the monopole mobility goes down. So if you're looking for a really responsive guitar, you need a low bridge mass just to keep the stiffness and mass down. And if you're looking for a high headroom guitar, you probably want a heavier bridge and a lower responsiveness, a lower monopole mobility.
All right, Trevor. There's a few more questions coming in here, and I'll just keep feeding them to you if you're okay with that.
Keep them going.
All right, so we'll just keep doing it, and they're kind of jumping around, so we may jump from one topic to the other if that's okay.
Yeah.
All right, let's see. Where was that last one here? Here from Donald Forsyth, down there in Georgia. Hey, Trevor, on a classical guitar, what effect does adjusting the mass and stiffness on the lower harmonic bar located beneath the sound hole have on the modes? I meant to ask this last October. Donald was here in Trevor's class here in October, so that's a great question. He calls it the harmonic bar. Some people call it the lower transverse brace. So,
yeah, well, it has quite an effect on the sound of a guitar, particularly the T112 mode of vibration. And if you start shaving away that brace, you will quite rapidly lower the T112 resonant frequency. So it's a good way of tuning the top. If you've got enough bracing in the lower bout, fan bracing, whatever you're using, to keep the distortions under control, that brace is quite an effective brace for helping tune the monopole mode of vibration, the T112. So if you shave it down, either make it thinner when you put it in or lower its height after you've got it in, it's a way of tuning the T112 frequency.
and Trevor, if you do that, how much will that affect your T111, which is your box resonance, and your T1113, which is your back resonance? Or does it mainly affect 112, just the top?
It mainly affects the 112, but because they all couple, it will have a small effect on the other two resonances, the T111 and T113. I suspect not enough to worry about, but if you're exactly where you want to be with a T112 and T113, it might be problematical. Generally, it's just going to, as you reduce the size of that brace, the T112 will lower in frequency, which will also drop the air resonance very slightly. It'll increase the separation between the T112 and the T113 because the T112 will drop faster than the T113.
Okay. This next question, Trevor, is about your falcate bracing design. And for those that are not familiar with falcate bracing, if you go over to the Luthier Academy website, click on the Falcate Bracing with Trevor Gore course, and you'll see that interesting design there for the top bracing. So I'll let Trevor kind of go into on what is the falcate bracing. And the question is from Vicente. In the falcate design, what is the function of the tertiary braces?
Yeah, okay. Well, the tertiary braces are the straight ones. If you stick the picture back up there, Robbie, if you can find it again. Yeah, thanks for that.
Mm-hmm.
Tertiary braces are, I can't point to these, they're the horizontal ones just above the bridge patch and the diagonal one in the lower bout of the guitar. And basically, they're just adding sideways stiffness to the plate. The two curved braces, the primary and secondaries, are taking the structural torque from the bridge. That's the string tension times the height off the soundboard. Whereas the tertiaries are basically providing some lateral stiffness on the sideways ones and keeping some bellying under control in the lower bout for the one down at the bottom end here, that diagonal one.
Okay. And Trevor, here's a comment from Jeremy, and I know the answer to this one too. This is just a comment about your books. Let's see, where did it go? I have been trying to buy that book, never in stock. Glad to know it's available on the Gore website. So I know you did a new edition here recently. You want to talk a little bit about that, and that it is in stock now and people want to order it?
Yeah, basically you can only get the book from my website. Stu Mac used to stock it. They keep on telling me they want to stock it, but they won't actually order any books from me, so they haven't got any stock at the moment. They might stock it again, I don't know. That's something we'll have to leave to them. So yeah, my website, it's been in stock since June last year, something like that. So plenty of stock available. Just order it straight off the website. Postage is not too bad to the States. It's usually $70, $80 Australian, which is about 50 US. So it's not such a bad deal. Unfortunately, I'm not Amazon and can't muscle over the...
Oh no, I think we lost Trevor there. Oh, he's back. Go ahead, Trevor.
Yeah. So basically, I'm not making anything on the postage. I just charge the rate that the post office charges me to dispatch them.
Okay.
So they weigh 4 kilograms, the book. So postage is never going to be cheap on something that weighs 4 kilograms.
That's right. All right, here comes another question. If I have a one string on a classical guitar that seems dead or less sustained than the other strings, is that a bracing issue or something else, or a combination of factors?
Well, if it's just one string, I'd suspect it's the string.
Yeah. So no wolf notes
note,
or...
it would be a different answer, but for one string, that's almost certainly a dead string.
So time to change your strings, right?
Time to change that one for sure.
All right. Here's a comment from David about thanks for the answer on wood selection Q and ARC. Very complete and helpful. That's from David. Good.
Yeah, thanks, Dave.
Just going through the list here. Let's see. This is from Alex. Let's see. Alex says, "Hey guys, are there any plans to turn the 3-day modal tuning masterclass into an online course?" Trevor, I'll let you tackle that one.
Robbie and I have discussed this at length on numerous occasions, and if we tried to do that, we've been daunted by the absolutely massive job it would be. It might happen, and it might not, because it is a seriously difficult task to actually video that whole course. Because I've actually tried it once before in the very early days. I've been doing this course now since actually before the books were published. I think the first course.
We seem to be having trouble with Trevor's in. Trevor, you're back again. You froze again there.
Yeah. 2009 was the first time we did it, and we tried to video it then. And the problem is that
I guess people in Australia are starting to come online, huh, Trevor?
Yeah, the Yeah, well, I won't go on about the fast internet we've had down here, because basically we haven't had fast internet until about 3 months ago. So it's early days on this stuff yet, and we're basically using a mobile line here. Mobile data is how this is getting transmitted to you. So it's not surprisingly a bit flaky. We're punting for fixed 5G, but we didn't get it. So we've got what we've got, and at least it sort of works.
Here's a comment from my buddy Paco there in Spain. Look at what he has to say. 80 people drinking from this fountain of free knowledge and only 10 likes. Come on, mates, and smash that bloody like button. It's free. Good day from Spain. Paco, I hope you're doing well. Boy, it's probably about midnight or later for you. So thanks for tuning in. All right, let's see. Here's one from Tony Rockwood. Tony was in your class here. He's in Elizabeth, Colorado. He was in your class here in October. Falcate bracing for smaller string guitar. How is the pattern modified when going from a large body to a small?
Well, not very much, basically. I use essentially the same bracing layouts on guitars from 390 wide down to 340 wide. That's millimeters maximum width at the lower bout. You have to sort of shuffle it around a bit, primarily to get the bridge position in the right place, but basically the pattern stays the same. There's a pretty simple rule about laying out your Falcate bracing, and that's just keep the segments about even in size.
All right.
Here's another segments between the braces. Yeah.
Here's another comment from David up there in South Dakota. Trevor, can you comment on the role of the higher body modes above Helmholtz in overall guitar sound or allure?
The higher body modes. Well, really, there's only one that makes a whole lot of difference, and that's the first partial of the Helmholtz. It comes in usually somewhere around 350 hertz, somewhere around that area, and you only hear it making much of a difference if it couples with the long dipole mode at the top. So you actually need those two to couple together. And a guy called Jürgen Mayer, Professor Jürgen Mayer, did a lot of work on this. I think it was the 70s, something like that, 1970s, where one of his findings was this: guitars with a high third resonance, or which displayed a third resonance, were preferred. And it took me a long time to figure out what this third resonance was, because if you look at the peaks of a typical guitar, the first peak is obviously the main air resonance, the Helmholtz resonance, so-called Helmholtz. Second peak is the T112, the main top resonance. Third peak is the T113, which is the back coupling through the top. Fourth peak is typically the cross dipole, and the fifth peak is typically the long dipole. What Mayer meant by the third peak was the long dipole, because the way he was exciting the guitar he was testing was, first of all, he didn't have a live back guitar, so he didn't see a T113. And secondly, he was exciting using a sort of stinger method, basically tapping, if you like, on the center line of the guitar. So he never saw a T112. Sorry, he never saw a cross dipole, a T21 either, because he was doing the excitation of a node of that mode of vibration. So it turns out that the third resonance is the long dipole, resonant frequency at about 350, 400 hertz, somewhere around there. And I think the reason why it gave a preferred sound was it was reinforcing the notes played on the first string, where the melody is often carried on classical guitars. So that's the only Helmholtz or the only body resonance that, other than the Helmholtz, that seems to make much difference. And if you get it to couple right, it is sort of worked. It sort of works. But I don't see it often in my guitars. I use another resonance to support the first string on classical guitars, and that's the cross tripole, which operates in a similar sort of frequency range and is a lot stronger radiator. But basically, what you need on a classical guitar is some resonance that supports the first string, and the only resonance other than the main air resonance that makes any difference is the first partial of that, which you only hear if it actually couples with a long dipole.
Okay. Folks, we're coming up on the end of the hour here. I always try and keep these things about an hour. If not, we start to lose people. So if you're going to ask a question, go ahead and get it in. I'm going to try and get to just a few more here. If you have a quick question, go ahead and pop it in the chat box there. Also, if you want to be eligible for the drawing, if you want to enter the drawing, click on that link at the top of the chat box there. Get your information in. So we're going to have the drawing here in just a couple of minutes. All right, Trevor, you got time for another question or two here before we call it quits?
Oh, sure.
All right, here comes one from John. John's also taking your class here. Is it very important to measure the frequency response curve on a guitar body with the neck attached or not? Or with or without strings? Does it matter? That's a good question.
Yeah, ultimately you want to measure the guitar fully strung up and ready to play, because that's actually how you hear the guitar. You only hear a guitar when it's in playing condition. So whilst the intermediate measurements will give you an indication of how the build is progressing and that you're heading for the right targets, really the only ones that matter are the ones where it's fully strung and ready to play. And actually stringing the guitar itself makes a difference to the frequencies you measure, because for a responsive guitar, the actual mass of the ends of the strings affects the resonant frequencies. So you've got to take that into account as well when you're estimating your way to your final position through the build process. I've actually got a slide on that which shows you how these things move, which we may get to if you want to actually see that.
I've pulled it up here. Is it in your PowerPoint?
It is indeed. Let me just get onto that. And okay, these are the critical spectrograms you get when you're building a guitar. So here's the guitar in the just box stage. So you can take your first spectrogram here. There is no bridge on this guitar and no neck. So it's just boxed up. Here the main T111, 112, 113 resonances. That's these three peaks here. You edge thin to help you get towards your target. And if you look at the two together, you can see how the frequencies have generally reduced and you've got more activity in the T111 mode. Then as you string the guitar, so you've now got a finish on, bridge on, strings on, you can see how the frequencies have moved downwards yet again. Here we've got the resonant frequencies, 92, 173, 224. Ideally, you'd want to be aiming for something like 170 here. So I put some side mass in to get it down and got to 91, 170, and 224. Now, all those frequencies are pretty well exactly off scale tones. So that's how the finished guitar is strung and weighted and how it sounds. If you look at all these together, you can see how you've progressively moved down. And what you want to do as you're building the guitar is to sort of map all these frequencies out until you end up in your strung condition, which is that one, strung and weights, with these resonances in exactly the right place. All right.
Okay. All right, here comes another question. We're coming to the end here, folks. Let's see. My recent build, steel string build, is very responsive, probably too responsive, very brittle or brassy. Is there a way of taming this to a more mellow sound?
Yeah, you can have a go. Try adding. I mean, that's what happens basically if you go too responsive. You end up building yourself a banjo instead of a guitar. So the way around that, if you've got in that situation, is to probably try adding some mass. So on those frequencies we were talking about, I'll see if I can get those up again. Okay, you got some target mode frequencies here, and I'm just going to guess at some numbers that you might have for a steel string guitar. Say you're at something like 95 and 170, presuming that you got it in exactly the right place. Try adding some mass and taking it down to 160. And you add mass by using some sort of poster putty. Just stick it on the bridge on the outside for trial purposes and see how you like the sound. Obviously, to get down from 170 to 160 is quite a lot of mass. And as you go through the 165 area, you'll be right on a scale tone and get a wolf note. So a bit of playing around with mass will give you some idea of where you can go to try and mellow the sound out a bit. As you go down in frequency for the T112, you get a sort of bassier, warmer sort of sound.
Okay. All right, let's go just one or two more questions and we'll go to the drawing. Let's see, how much does the velocity of sound affect the sound of a guitar?
Well, it does affect it. I mean, we've had that crazy situation where, as some of you will well know, having been to the modal tuning course, I show a few pictures of where I live, and I live right at sea level. And when I say right at sea level, at this very moment in time, the ocean is about a meter below my feet. So when I say sea level, I mean sea level. When I come to Parker, things are a bit different there. I tune my guitars here at sea level, go up to Parker at 6,000 feet, and all the resonant frequencies have changed because the air density has changed and the speed of sound has changed. And what was interesting was when I first discovered this, I had some guys in the workshop. I think they were NASA engineers. There's always a NASA engineer or two in Robbie's courses. And I said, okay, guys, let's look up the speed of sound and the density of air at 6,000 feet. And I had the 4 degree of freedom model open, and we plugged in the numbers for the speed of sound and air density at 6,000 feet. And the model predicted exactly the level of change that we had in the guitar from it being tuned at sea level to 6,000 feet. So yeah, it does make a difference, and basically it alters resonant frequencies, mainly the main air resonance, the Helmholtz mode, so to speak. But because that resonance couples with all the others, it alters all the others as well. So you need a 4 degree of freedom model to figure out what's going to go on if you want to play around with that.
All right, we're getting close to the end. Man, these questions you keep rolling in here, Trevor. So I'm going to try and get to as many as I can. Here's a very quick one. Let's see. Making a very small guitar at the moment, would a 170 hertz frequency or 180 hertz frequency for the top work well? If so, how do I shoot for it? Boy, that could go into a book on that. Hey, I think you wrote a book, didn't you?
Yeah, you can probably get to 180 hertz on a low bout with the 350. I mean, that's not a desperately small guitar. My is this a steel string guitar? Doesn't say.
Doesn't say.
My small body classical is 340 in the lower bout, and I typically tune that down at 90, 190. So that's 90 air resonance, 90 hertz air resonance, and 190 T112 resonance. So that works fine. Obviously, trying to get a very low frequency for your main air resonance out of a small guitar gets harder as the guitar gets smaller. But it's possible. You just got to make your panels somewhat floppier, but also respect the rule of thumb: keep 4 semitones distance between the T112 and the T113. If you drop the T112 too close to if you drop the T113 too close to the T112, you'll get them fairly messy, muddy sounding guitar, which doesn't work too well.
Right. All right. Here's another one. Kenneth, thank you, Robbie and Trevor, for a great session. Can you please address live backs versus non-live backs? I think you touched on that just a few questions ago, but maybe reiterate.
Yeah, that's right. So in very rough terms, a live back will give you more peaks in the frequency response curve, not just the equatable to tone, if you like. So having a live back gives you tone. If you have a non-live back, you're not robbing the sound energy from the top, which is where most of the sound radiation comes from. You're not robbing that if you're using a non-live back. You're not robbing it to drive the back. So as a consequence of that, there's more energy gets radiated from the top. So a live back gives you tone, and a non-live back gives you volume.
All right, perfect. Folks, this is golden information. Just that sentence alone is golden information, folks. So take advantage of it. I'm going to do this one and one more. Do you change the sound hole diameter depending on what the top frequency has measured? Maybe just talk a little bit about what the sound hole does as you make it smaller or larger.
Yeah, I mean, when you're measuring the top frequency, we're talking about the T112 frequency here. If you change the sound hole diameter, yes, the T112 frequency will change, but not by very much. What you're primarily changing with sound hole diameter is the T111 resonance, the main air resonance. The smaller you make the sound hole, the lower the main air frequency is. And that couples with the top, and the top will come down in frequency a little bit as well. But if you want to alter the T112 frequency, operate on something more directly on the top is probably the best way of doing it.
All right. And here we go with our final question. When you build after all this time and study, do you focus more on the sound as you build, or stop and tightly check frequencies at periodic steps?
Well, you got to start with the end in mind, and so you got to target where all the frequencies need to end up, and you make sure they all end up there. And I do that through that sequence of spectrograms that I showed before, heading down and tweaking things exactly what details you're doing, or how much of a particular detail, for example, edge thinning, you do at a particular point in time to make sure they get to the frequencies you want. So things to keep in mind are the monopole mobility you want to end up with, and the resonant frequencies you want to end up with, and come down towards those. And if you get those right in the places where you want them, and you've picked good numbers, you will have what I might call a 99% guitar. That is, by any standards, a really good guitar. If you're looking for absolutely supreme, great guitar, some of that's just down to luck. Some guitars do sound extraordinarily different from others. And I'm talking about the sort of 1 in 100,000 style guitar here, which you don't hear very often, and most people won't have heard at all. And it's very hard to say why those special guitars are particularly special. I think it's something to do with the damping in the wood, because I can measure everything else, but damping is a bit of a difficult thing to get a handle on. And as I say, you can make a really nice guitar just by getting the major resonant frequencies in the right place and the monopole mobility right. You get a really, really good guitar out of that, but there's still a sort of special level beyond those, which is a bit of the black art of guitar making.
Perfect. All right. Thank you so much, Trevor. If you guys want to take this a step further and go down that rabbit hole, go over to Trevor's website, get his books. Also on the Luthier Academy website, you have 2 courses, Falcate bracing, guitar analysis and testing, and it will, I guarantee it will make a better guitar. I've sat in, like I said, on Trevor's classes 11 different occasions, and my guitars have become better because of it. Trevor, you think we should give something away?
Oh, absolutely.
All right, so we're going to give away one of each of those courses, Falcate bracing and guitar analysis and testing. That means we have to go all the way down to São Paulo, Brazil, and wake up Cesar and Manuela. They're probably asleep by now, but let's check in on them. There they are. You're not asleep.
No.
It's starting to get pretty late for you down there. What time is it?
Yeah, it's a little bit over 9 of the night.
Okay. All right. So let's go ahead and do a drawing. Let's do the guitar analysis and testing one first.
Okay, Manuela.
Let's see. The winner is
Chris. All right. Number 43. Look at that.
yes.
Very good. All right. Congratulations. You have won the guitar analysis and testing. All right. Our next giveaway is going to be Trevor's Falcate bracing course. And everybody I have talked to that has used that said that it was a great guitar that they built with it.
And the winner is...
Oh, Paco.
Paco, no!
Congratulations.
Congratulations.
Oh, Paquito, already over there in Ubida, Spain. Congratulations, you have got the Falcate bracing course. So I expect to see a Falcate flamenco guitar in the future. All right, thank you, Cesar and Manuela. Very good.
Thank you.
Yep. Thank you, folks, everybody, for tuning in. And thank you to Dr. Trevor Gore for taking time out of his busy day over there in Sydney, Australia. A nice round of applause for him. Come on, folks. There we go. All right. Thank you very much, folks. Trevor, anything you want to add? Should we just call it quits?
I think we'll call it quits, but thanks very much, everybody, for joining in, and thanks for your insightful questions.
All right. Thank you, folks. Over and out. We'll see you next time.